Einstein's theory of relativity and black holes, reality or fiction? Are science fiction writers nuts, or was Einstein truly ahead of his time? As children, we all saw and laughed at Einstein's iconic tongue-out photo. But this weird-looking man had some genuinely wild theories which he admitted were too preposterous to be true, making us laugh less as adults. His most renowned work is the theory of relativity. Einstein's theory of relativity transformed our view of the universe and its mechanisms. It demonstrated that time and space are relative to the observer's perspective, rather than absolutes. We can now create better models of the cosmos that account for the effects of speed and gravity, which are both relative to the observer. It has allowed us to explore and understand the universe in previously inconceivable ways. Its consequences extend well beyond science and into our daily lives. Do you believe that the Global Positioning System, GPS, uses relativity principles to accurately compute your position on Earth? Let's go over the facts behind every science fiction book you've ever been fascinated with comprehending at 3 a.m., which undoubtedly led you to view this video. The theory of relativity has startled experts and laypeople alike. It basically says that the cosmos isn't as absolute or substantial as it appears. Instead, it is always changing, and the idea of time and space is relative to the individual perceiving it. This means that two persons who see the identical events in different places of the world may have very different perceptions on the occurrence. If you close your eyes and envision a black hole, I assure you won't be far from replicating how insane it truly is. You'll probably envision a massive black spot in the sky engulfing everything that gets close to it. Well, it's not that easy. Black holes are one of the most interesting phenomena in the cosmos, and Einstein's theory of relativity explains why they exist. Black holes arise when a huge body, such as a star, collapses under its own gravity. This concentration of mass generates a zone in space-time where gravity is so powerful that nothing, including light, can escape it. The event horizon refers to the surface that divides the black hole from the rest of the universe, also known as the point of no return. Beyond that point, the laws of physics cease to apply. The general theory of relativity predicts how space-time behaves around a black hole. First, let us discuss how black holes affect space. According to the general theory of relativity, space-time around a black hole is distorted, resulting in a tremendous gravitational field that can bend light. This gravitational field generates a lensing effect, distorting light from neighboring objects and allowing it to focus on a specific spot. From the perspective of an observer outside the black hole, light from sources near the event horizon looks warped and focused in a specific location. This is called a gravitational lens. Furthermore, light leaving this gravitational field is stretched, appearing redder as it travels further away from the source. This is referred to as the gravitational redshift. Gravitational lensing has grown in popularity and importance in astronomy because it enables astronomers to investigate objects that would otherwise be too faint or distant to observe. Similar to a lens used to decipher smaller written text on a mystery piece of paper discovered by the water. Doesn't that make you curious? Astronomers can better examine some of the universe's most distant, powerful, and mysterious phenomena if they grasp how black holes form gravitational lenses. This situation can be utilized to investigate the properties of dark matter, which makes up the majority of the cosmos, as it influences the form and size of lensed images. Gravitational lensing can also be used to measure the size of galaxies and track their evolution. Now let's look at the impact it has on time. Ever heard of the twin paradox? The twin paradox is a thought experiment about two twins, one of whom embarked on a space mission. When he returned to Earth, the twins discovered that the one who remained at home was significantly older than the one who had journeyed. Did you expect that? I do not think so. And nobody did. But how could this happen? This effect is known as time dilation and can be explained using the theory of relativity. As previously stated, gravity and velocity alter space-time, causing time to flow at varying rates based on the observer's perspective. This indicates that the twin who traveled was subjected to stronger gravitational pulls and faster velocities. Therefore, his sense of time would have progressed significantly slower than the sibling who remained at home. Similarly, and with even greater gravitational power, time slows around the event horizon, coming to a halt at the singularity or point of infinite gravity at the center of the black hole. Returning to the crazy twin dilemma, NASA decided to undertake an experiment on real-life twins to test the thought experiment. They sent one astronaut, Scott Kelly, on a year-long mission to the International Space Station, while his twin brother remained on Earth. Before the flight experiment, they gathered samples from the brothers to compare with when the astronaut returned. Blood sample comparisons revealed that the astronaut's telomere length, a DNA parameter associated with human longevity, had increased by 14.5% while aboard the International Space Station. A correlation was found between an individual's telomere length at age 25 and their lifespan. Those with longer telomeres outlived those with shorter telomeres. Crazy, right? After 190 days, his telomere length had returned to normal. Studies are being undertaken to confirm that this occurred due to the time dilation phenomena. Another concept associated with the theory of relativity is the wormhole. Wormholes are hypothetical tubes in space-time that connect two distant points in the cosmos. According to theory, a wormhole might be exploited to decrease the distance between two locations in the universe, allowing for quicker travel than light. This may be used to establish a shortcut for a space traveler or to investigate portions of the cosmos that are too distant to visit in a human lifetime. Although wormholes have yet to be verified in practice, the concept is based on relativity and has piqued the imagination of numerous science fiction writers and space enthusiasts. There is also the possibility of using a wormhole to produce time travel, albeit this is a very theoretical concept that is still being debated. So far, all we can do is write about it. Until now, the general theory of relativity has been verified correct in all tests done by physicists. This theory is the foundation of our knowledge of space, time, and gravity. It has supplanted Isaac Newton's concept of gravity as an instantaneous power acting from a distance. Furthermore, research into the cosmic microwave background has revealed that supermassive black holes, millions of times more massive than the Sun, exist in the centers of numerous galaxies. While observing a black hole's singularity is impossible, studying its repercussions on the space-time around it can provide insight into this elusive and amazing phenomena. I'm sure you're asking if any concrete consequences were obtained and observed from the follies you've heard so far. Since its inception, Einstein's theory of general relativity has served as the foundation for modern physics, with astronomers attempting to establish its correctness. During the famous 1919 solar eclipse, scientist Sir Arthur Eddington confirmed that the sun's gravity can bend light from stars, as we previously explained under the effects of gravity on light. A new study has used gravitational waves to help support the theory of general relativity. Gravitational waves are small wavelets in space-time produced by the catastrophic collision of two enormous objects, such as black holes or neutron stars. The study examined gravitational waves emitted by a neutron star merger and discovered that the data precisely matched Einstein's predictions. This new study adds to the overwhelming evidence that Einstein's theory of general relativity is valid, and that gravity has the ability to bend time and space as predicted. In 2016, the LIGO, or Laser Interferometer Gravitational Wave Observatory team, found a phenomenon of merging black holes when they received a signal from two black holes 2.3 billion light-years apart. The signal was discovered by two interferometers in Louisiana and Washington, and then further studied to determine its parameters. The signal was consistent with the predicted qualities of two black holes merging together, and scientists had never witnessed such an extreme illustration of general relativity in action. The signal was consistent with the predicted behavior of two black holes orbiting each other, gradually becoming closer together before merging into one. Scientists were surprised to see that the black holes were wobbling 3 times per second as they orbited each other, an effect predicted by general relativity but never observed before. This phenomena, termed as frame dragging, is created by black holes generating a warp in space-time around themselves. This distortion led the two black holes to wobble as they orbited one another. The discovery of two black holes merging and wobbling at a rate of 3 times per second, as predicted by Einstein's theory of relativity, is extremely astonishing, and it sheds new light on one of the most powerful equations ever written. It not only confirms the validity of general relativity, but it also demonstrates that the world is stranger and more enigmatic than we can fathom. The possibilities linked with the theory of relativity are absolutely astounding, and the findings of this study serve as a reminder of how much we still have to understand about the world and its enigmatic workings. Whether investigating the vast reaches of space or debating the feasibility of time travel, the theory of relativity is a critical piece of knowledge that will allow mankind to continue exploring the cosmos and discovering its secrets. Alright everyone, that is all for this video. Thanks for watching. I hope you liked your short trip with us. Don't worry, your telomeres are okay. And remember to like, share, and subscribe.